Greetings to all the viewers. The session is going to deal with chemical sciences, CSIR, NET, GRF, a previous year question paper. This will be helpful for your preparation towards government examination preparation like degree lecturer, junior lecturer, or else university professor post. So if you're applying for, and also the kind of competitive examinations, entrance examination, if you are preparing for GATE, state eligibility for teaching, and also kind of conceptual based reasoning, logical questions in the chemistry, and also the kind of what if you are aspiring for the research in the chemistry, that kind of content is also available at the channel Dr. Kavitha Chemistry Academy. Earlier it will be World of Competitive Chemistry, right? So here you can subscribe the channel, watch the channel regularly, and share with your friends. You will get the new content every day. Consider the following reaction. So this is the one we taken from this CSIR NET previous question paper, June 2025, right? So here series of sessions already conducted which available at Dr. Kavitha Chemistry Academy. Now we entered into the question number 63 over there. So earlier questions, earlier previous solved papers available at this channel. So let me introduce this today's session. Here is the question related with the inorganic chemistry. Consider the following reaction. I'm taking the octahedral complex of chromium carbonyl complex. Here you can find octahedral chromium carbonyl compound that can be treated with X. Upon heating, there is a provision for dimerization. Whenever 2 moles of chromium carbonyl complex was taken, there is a dimerization taken. Moreover, it is converted into an anionic dimeric complex. Initially, it is the neutral monomeric complex. After heating with certain kind of compound, here the formation of dimerized anionic complex got generated. Here what could be X we need to identify. So this X to be identified, 4 options are provided. In order to answer this one, we have a detailed explanation over there. In order to understand this reaction, the correct answer will be H minus. H minus is designated as a hydride ion. Hydrogen accompanied with the negative charge is called hydride ion. So how it will satisfy that kind of dimerization process, let me show. So 2 moles of chromium hexacarbonyl compound was taken, added with X. That is unknown as of now. And heating is susceptible for the dimerization process, so that here the formation of HCr taken 5, CO taken 10 minus formation taken, simply the dimeric product. During the reaction, the product contains a bridging hydrogen that is called mu hydrogen. Always bridging ligands in the coordination complexes are indicated with the mu. So mu hydrogen between the 2 chromium atoms and carries overall negative charge. So there is a provision for negative charge over the hydrogen, then only complex is acquiring negative charge. So that's the reason why from this data only simply we can reveal X is equal to H minus, that is hydride. If you're writing like that, 2 moles of chromium hexacarbonyl added with hydride ion upon heating, there is a provision for dimeric product formation. So if you're counting electrons in the initial and final complexes, your chromium hexacarbonyl initially 18 electron complex and more stable. So 18 electron complex it will be. So dimerization, each chromium loses one of the carbonyl ligand, giving chromium CO taken 5 only. During the dimerization, actually here 2 moles here, the requisite product also contains 12 carbonyls, but here we got a fever of carbonyl, that is 10 carbonyl groups are present, 2 are lost during the dimerization process. That's the reason why during the dimerization one of the carbonyl lost per each chromium. It is becoming chromium CO taken 5 only. And moreover, hydride ion is bridging 2 chromium atoms. Chromium bond also generated. There is a provision for one of the direct metal linkage. In either bridging hydride is also linking 2 chromium atom. This is the way a kind of dimeric complex is originated during this product formation. That's the reason why chromium-chromium bond is formed, resulting in the complex occupying 18 electron configuration, and the bridging metal hydride complex it will be, so that HCr taken 5, CO taken 10 minus is having 18 electron rule, so that it is also the stable anionic complex. That's the reason why, according to all the information whatever we gathered, so here X is hydride ion, that is given in the option number 2. So here option number 2, H minus, is the correct answer. For question number 63, option 2 will be the correct answer. Move on to question number 64. The correct statements regarding the olefin polymerization involving metallocene and alkyl aluminum species from the following, right? So here we are taking alkyl aluminum species and olefin polymerization process of metallocene was taken. Traces amounts of water cause a significant increase in the rate of ethylene polymerization by CP2TiETCl. That is nothing but a complex of titanium and aluminium Et2Cl. So here chlorodiethyl aluminium system. Methyl alumino-oxane indicated as MAO is employed as an activator for the catalyst CP2ZrMe2, zirconium compound it will be. Then here we have boron C6F5 taken thrice. Your trialkyl boron is an activator for CP2ZrMe2. The termination step of the polymerization reaction is the beta hydride elimination. If beta hydride elimination taken, there are two possibilities. One is one growing chain will be terminated by means of alkene formation. In either this is the way beta hydride giving rise to unsaturated compounds. So let me see what kind of answers are correct related with the olefin polymerization involving metallocene and alkyl aluminum species. So if this is the case, the possible answers are A, B, C, D. All four answers, whichever given, all four options are exactly correct related with this kind of olefin polymerization process. Let me show how can we explain all four options are correct. First of all, statement A is mean for traces amount of water increase the ethylene polymerization rate. Whenever moisture conditions are present, polymerization got amplified. How can we justify this answer? Let me see. In the CP2 titanium ETCl and aluminum ET2Cl system, this is the kind of titanium aluminum catalyst compound. A small amount of water can activate the alkyl aluminum species and increase the concentration of active titanium species, right? Whenever moisture is present, aluminum and titanium species both got enhanced, both catalytic activity got enhanced. Therefore, trace water can significantly enhance the polymerization rate. As the activity of the catalyst is more, obviously rate of the reaction will be rise. That's the reason why both are more preferable under aquated conditions in the traces amount. That's the reason why statement A, what they are saying, is exactly correct. Let me go through the statement number B. MAO activates CP2ZrMe2, right? MAO mean for methyl alumino-oxane. Methyl alumino-oxane is a very common activator, co-catalyst for metallocene catalyst. So whenever co-catalyst was taken, co-catalyst is the kind of chemical substance which having tendency to rise the activity to fasten the catalytic activity of actual catalyst. That is called co-catalyst. In the presence of co-catalyst, efficiency of catalyst got elevated. So here this methyl aluminum oxide is a co-catalyst for metallocene catalyst. So CP2ZrMe2. So this is a kind of catalyst activity got uplifted by this one, right? So here MAO abstract a methyl group to generate a highly reactive cationic zirconocene species. Whenever CP2ZrMe2 was taken, cyclopentadienyl anion. Cp stands for cyclopentadienyl anion. If 2 was given, 2 such ligands are present around the zirconium. Right, MAO already you know, methyl aluminooxane. So if these two got mixed up, how the activity got enhanced? By means of transfer of methyl group. Here we already had 2 methyl groups around the zirconium that will be shifted towards MAO, so that here there is a positive ionic complex is originated around the zirconium, and MAO is accepting methyl. Here is the formation of negatively charged anionic complex. This is the way zirconium complex activity got uplifted by releasing one of the methyl group to this MAO. So it is also the correct representation. B is also right representation. Let me move on to option number 3. Option number 3 was given as trialkyl borane activates CP2ZrMe2, right? So again here cyclopentadienyl anion zirconium complex was given, dialkyl. Here dicyclopropyl, dicyclopentyl anion, and here dimethyl zirconium. This complex was taken, the 4 coordinated complex it will be, whenever it is in contact with this trialkyl borane, so that activity got uplifted. Let me show whether it is correct or wrong. A strong Lewis acid, obviously we aware about this one. Boron, trialkyl borans are said to be Lewis acids. How can we explain that one? There are 3 covalent bonds around the boron, and still there is a short of 2 electrons, so that there is a probability for the vacant orbital to accept the electrons from the basis. That's the reason why there is a provision to accept the electrons, which is indicated with the Lewis acidic nature for this trialkyl borane, but having tendency to absorb the methyl group. Again, same like earlier aluminum complex, even aluminum is also the kind of Lewis acid, right? So here is also methyl group taken by this borane. So that here again there is a provision for the cationic complex around the zirconium, and by accepting this methyl by the boron, there is an anionic complex just like MAO. So here is also the provision for the activation of this complex, zirconium complex, for this polymerization process. Option C, what they are saying is exactly correct. Let me go with option number D. Termination occurs by beta hydride elimination. Beta hydride elimination always giving rise to a kind of olefinic compound. Double bonded compound will be originated. So here during the metallocene catalyzed olefin polymerization, chain termination occurs by beta hydride elimination. Whenever we are taking, this is the metal. Metallocene is nothing but any metal direct contact with alkyl chain, metallocene complex will be generated. That metallocene complex is having a longer chain over there. So whenever we reach the requisite length of that polymeric chain, we need to go with the removal of the hydrogen from the beta position. With respect to metal, adjacent carbon is alpha, and the next is said to be beta. Beta carbon is susceptible to release one of the hydrogen. Whenever hydrogen got released towards the metal, there is the origination of metal hydride. And subsequently, this alkyl chain is becoming like a olefin over there. Terminal carbons are becoming unsaturated double bonded one, so that chain length got stopped. That is said to be termination, stop of the reaction. So that polymerization reaction got ended over there. The growing polymeric chain transfer beta hydrogen to the metal, producing metal hydride. Olefin termination taken place at the polymeric chain, so that D is also correct statement only. This is the way whatever they are mentioning in all 4 options are exactly correct. So for this olefin polymerization through the metallocene activation, this possibility is exactly correct. So option number 1 is the correct. All 4 options are satisfying over there, A, B, C, D. So option 1 is the correct answer for this question. Let me move on to next question. List 1 contains the metal alkyl compounds which do not undergo beta hydride elimination step, and list 2 gives the reasons. So here, metal complexes were given. Again, it is the part of organometallic chemistry, subject of inorganic chemistry. So here our metal complexes are provided. Here is a kind of reason behind that kind of reaction. Beta hydride elimination process is mentioned over there. Here is the platinum complex. You can notice most of the platinum complexes are square planar. Here are two ligands around this platinum, and this side you can notice the cyclopropyl chain. So this is the kind of platinum complex provided over there in the A. B is having cobalt complex. Here you can notice the kind of octahedral complex around the cobalt. Here we have kind of diamino, and there is a provision for the hydration at this terminal, and here we have a hydroxyl group on the nitrogen, and this nitrogen is having a hydroxyl group again, and here is the provision for this nitrogen with oxygen bond. This is the way a kind of octahedral compound got originated around the cobalt, where you can notice a kind of what kind of compound it is, dimethyl ethylene diamine, and here we have NOH like this. So this is the way a kind of octahedral compound we had, and here is the bridgehead compound called a kind of puckered ring system. Narbornine polycyclic ring system is provided. You can notice a 6-membered ring like a cyclohexane over there, and here is the kind of another 1, 2, 3, 4, 5, 6-membered ring once again, and both are connected with another methylene group in between, so that it is a polycyclic ring system. You can notice 3 rings within and metal linked with that, so that here is also the kind of organometallic complex, and here is the metal linked with the open chain molecule. This is the molecule, this is the one, this is the kind of alkyl chain, which is the open chain one. These many provisions are provided. List 2 or some reasons are there. Then what kind of match exactly go with this kind of information? For beta hydrogen elimination reaction, we need to identify. For that purpose, we have a detailed explanation over there. Characteristic of beta hydride elimination. Beta hydride elimination is a common decomposition process in the transition metal complexes. After the beta elimination process, there is a formation of alkene is possible. Alkene will be the final product over there. Requirement 1. In order to go for the beta hydrogen elimination, first requirement will be alkyl ligand must possess hydrogen atom and the beta carbon atom. So beta carbon must possess the hydrogen atom, and it is into the alpha carbon which bonded to the metal, right? So beta hydrogen must be present over that metal alkyl compound. That is the first essentiality. Being beta hydride elimination requires hydrogen at the beta position. That is the compulsory condition. Requirement number 2, the metal center must have empty coordination site. So here metal must be a kind of Lewis acid they are saying, then only there is a provision to accept this hydrogen whichever released from the beta position of the carbon. That's a reason why a metal center must have the empty coordination site. A vacant orbital should be present in order to accept that beta hydrogen in the transition state. This means that metal complex is typically electronically unsaturated, right? So here metal complexes are electronically unsaturated. That condition will be provided, so that metal must contain empty coordinated site on the valency orbital. And another requirement will be a coplanar transition state is often required, involves the metal, alpha carbon, beta carbon, and beta hydrogen as well. So that 4-member cyclic ring transition state requires a coplanar transition state. So metal with respect to alpha carbon, beta hydrogen, 4-member ring system will be originated that able to adopt roughly syn periplanar arrangement. All the atoms are arranged in the one side, so that syn periplanar arrangement is provided with that one. So it's a kind of a coplanar transition state. This is also another requisite condition in order to go for the beta hydride elimination. Requirement number 4. The resulting alkane must be able to form without violating Brett rule. It states that double bond cannot be formed as a bridgehead position in the small bridged cyclic system. If the elimination leads to the bridgehead alkane, the reaction is prohibited. So here, bridgehead carbon acquiring the double bond must be prohibited. That is called a Brett rule. So Brett rule must be followed in order to go through this beta hydride elimination process. If Brett rule is violated, there is no provision for the formation of alkene within the compound. So that this is also essentiality for this beta hydride elimination reaction. If four requirements satisfied by that compound, then only beta elimination will be fulfilled. Proceeded. Now, let me go with the complex. First one, there is a complex of platinum. Once edge, you can notice the two ligands in either side. Cyclobutyl ligand is also present. So whenever this square planar complex taken into the consideration, a complex of platinum plus 2 cyclobutyl often square planar and beta hydride elimination to occur. Platinum alpha beta atoms are need to align in the syn periplanar transition state. Due to the rigidity of the strain of the compound, alpha beta carbon atoms are constrained, and platinum C alpha, carbon alpha, carbon beta, hydrogen beta coplanar transition state is may not be suitable for this kind of complex, so that it will resist for that kind of transition state, so that if requirement is not satisfied, obviously there is no provision for that kind of complexation, and beta hydride elimination may not be possible, so that planar transition state is not accessible. It is the right answer for the absence of beta hydride elimination reaction for this platinum complex. Then cobalt complex with the C2H5 ligand. Next, we had that six-membered ring system octahedral complex was there, where you can notice the ethyl ligand within. Ethyl ligand is having a kind of beta hydrogen, obviously, but cobalt complex 5 ligands, 4 on the cobalt macrocycle, and 1 is the water, and another is the ethyl group, making D6 plus 3 complex. So here cobalt plus 3 complex are typically 18 electron in nature. Cobalt center is electronically saturated. The second condition is violated over here. What condition? Cobalt are not only cobalt, but the metal whichever participating in the organometallic complexation must possess vacant site. Then only beta hydride transfer is possible. Then only beta hydride elimination is possible. If this is the cobalt complex where 18 electron is perfectly satisfied, that indicates what? No vacant site over there. That's the reason why no vacant coordination site over the metal. There is no provision for the beta hydrogen transfer for this. So this cobalt complex may not accept that beta hydride elimination, being vacant orbital is absent for this. Option B is violated due to that reason. Metal complex of this bicyclo, we had that polycyclic ring system. The third one, polycyclic ring system, was there. Bicyclo 2,2,1 heptyl nor bornyl ligand was there. So that that is linked with the metal. So this kind of bridgehead compound directly linked with the metal. If that is the case, alpha carbon atom is CH secondary and beta carbon is the bridgehead carbon. Here, as we already aware, requirement number 4, Brett rule must be satisfied in order to go for the beta elimination reaction. Brett rule mean for bridgehead carbon, if participating in the double bond formation, that kind of beta elimination is totally prohibited. That's the reason why here is the beta carbon. In case of this metal nor-bornyl complex, we are having bridgehead carbon position provision for the double bond formation in accordance with the Brett rule. That is a highly sterically strained one, so that your leads the bridgehead olefin, which is perfectly prohibited, so that there is no provision for beta hydride elimination. Now move on to metal complex with the CCH3 taken thrice, tertiary butyl ligand if present. There is no option for the beta hydrogen, right? The tertiary butyl group is attached to the metal via the alpha carbon atom. Beta carbon is 3-methyl groups. Okay, there is a provision for the beta hydrogen, obviously. Beta carbons do not contain any hydrogen. Beta carbons do not contain any hydrogen atom. They are fully substituted with methyl groups only. Since there is no beta hydrogen available, beta hydride elimination cannot occur. So in case of this tertiary butyl group, let me go with that one first. Let me see. Yeah. So with respect to this one, compound number D, metal directly linked to the carbon called alpha. At the beta carbon atom, you can notice 1-methyl, 2-methyl, 3-methyl. In order to satisfy the tetravalency of the carbon, beta hydrogens are lacking. If beta hydrogens are not present, obviously there will be no provision for that beta hydrogen elimination, beta hydride elimination. Requirement number 1 is failed to satisfy. That's the reason why here the beta hydride elimination is not possible. So the reason complex and the reason to be perfectly matched we need to go with. So if first one is the platinum complex, here the sterically strained ring system is there. A planar transition state do not be accessible for this one. So A is mapping with P. Then let me go with the second one, cobalt. Cobalt complex is taken into the consideration. So here cobalt complex perfectly satisfying 18 electrons rule, so that no vacant coordination site is available at the cobalt plus 3 complex metal ion. So if vacant orbital is not there, hydride transfer is not possible. Be with mapped with this Q. If you are taking this metal directly linked with this bridgehead Narbonne system, leads to the bridgehead olefin formation. So the carbon which ever present, bridgehead carbon is participating in that double bond formation after the beta hydride elimination, that is perfectly prohibited in accordance with the Brett rule. That's the reason why C with R is only the correct reason. If you go with the D, metal linked with the alkyl chain where the beta carbon lacks the beta hydrogen atom. Beta carbon hydrogens are absent. That's the reason why here the beta hydride elimination is not possible. D with S only. So direct linkage, direct reasons are manifested. So A with P, B with Q, C with R, D with S provided in the option number 1 only. So for this question, option number 1 only the correct answer. First one is the correct answer. Move on to next question. Question number 66 we are discussing here. The correct number of stereoisomers and correct number of enantiomeric pairs adopted by cobalt triene Br2 positive. If this is the complex, so cobalt triene Br2 positive, this complex is having triethylene tetramine. Triethylene tetramine is the ligand provided, and Br2 bromine is also another ligand, and there is a positive charge over the complex. If this is the complex, possible stereoisomers and number of enantiomeric pairs to be calculated. For that purpose, we have definitions initially. Later on, we will go for the calculation, right? So stereoisomer mean for the isomers compounds with the same molecular formula, but the sequence of bonded atoms will be differed. The differs in only the three-dimensional orientation of their atoms. Around the metal, how the orientation changes, that only the matter for the stereoisomers. Their position matters for the stereoisomers. Stereoisomerism is classified into two main types, enantiomers and diastereomers, which include the geometrical isomerism. Right here, the geometrical isomerism is also the part of stereoisomerism only. Chirality. Chirality is the key property for the optical isomerism. Molecule is a chiral if it is not superimposable on its mirror image, right? So if two molecules were taken and one upon another, if non-superimposable, then only we can say it is optically active, right? Chirality is meant for that kind of important category for the optical isomerism. So any compound with any carbon with 4 different functional groups around that one is called chiral carbonate. Enantiomers. A pair of stereoisomers, non-superimposable mirror images to each other are called enantiomers. Whenever you are taking two different isomers which are mirror images to each other, whenever one placed upon another, there is no superimposability. Those are having an enantiomeric relationship. They possess identical physical properties like melting and boiling points, and their chemical property will be entirely changed, and plane polarized light rotation will be different. One of the isomer is moving in clockwise direction, another isomer is moving in anti-clockwise rotation, this plane polarized light. Enantiomers rotate plane polarized light by equal magnitude in the opposite direction. Dextrorotatory means positive rotation, levorotatory means negative rotation is possible. This is about enantiomers. Enantiomeric pair. One set of enantiomers, each are mirror images to each other, and half of the number are one chirality like dextrorotatory, another is levorotatory. The stereomers are stereoisomers that are not mirror images to each other. They generally contains different physical properties and chemical properties as well. This is about what concept behind the question. So these must be known, then only we can go for the calculation of stereoisomers and enantiomers, right? The complex whichever provided is cobalt triene Br2 taken positive. So here is the complex said to be triene if taken. If the triene if taken is a kind of A type of complex, being it is taking part of four bonds with this metal. It's a tetra coordinated one. So that, and here we have two bromines. Bromine is monodentate ligand. That's the reason why each bromine directly linked with this one. So simply it is represented as triene is binding with this metal with the four bonds. That's why tetradentate ligand it will be, and each bromine is the monodentate ligand. Hence you can achieve a octahedral complex over there. The provision to write the octahedral complex, in order to simplify, all the triene is represented as AAAA and Br2 with B2. So this is the way all four A's are represented in the left hand side, two bromines on the right hand side, and it's a mirror image if written. Both are having the relationship called enantiomers. And moreover, if both the bromines are on the same side, it is the kind of cis form, obviously. Cis form will be there. And coplanar ring is absent within the complex. Now, let me go with all four ligands are indicated. Tetradentate ligand is indicated over there. In between, you're drawing this bromine atom. So here, one of the tetradentate ligand is axial, and one of the bromine atom is axial, and another bromine is equatorial bond, right? So if around the metal, the ligand is a right angle, that is said to be axial bond. So here is one of the A bond, one of the B bond is existing in the form of axial bonds. Again, it is the octahedral complex only. Let me represent it's a mirror image. When these two mirror images are represented, obviously you can go through the enantiomeric pair. These two are called enantiomers only. Again, there is a provision for the representation in a cis form, right? Again, it is the cis form only. And moreover, it is called a beta form. Why you are saying beta? Because here one of the representation alpha initially, where you can notice two bromines adjacent one side by side to each other. But in case of this one, we got slightly separated both the bromines, and here is the beta form you can notice. And this is the coplanar ring system. And another provision, we have another provision. Let me occupy all four tetradentate ligand in all four axial corners, and all four equatorial corners. Two bromine atoms are occupying the axial positions around the metal. Again, it is the octahedral complex only, but the provision for the representation two bromines are entered with respect to each other. That is called a transform. And the three coplanar ring systems are a chiral. based on the plane containing MA4 is the symmetry is in the symmetry of the plane. So here symmetry operations, if you're performing within the compound, simply you can bisect the molecule from this what we can say, this is the horizontal plane. So symmetry elements are perfectly present. Simply you can make the two identical halves with this. That's the reason why achiral it will be. Here is also the kind of achiral. You can go with the vertical plane over there so that achiral compound will be originated. This is the molecule said to be achiral. Whenever the molecule is said to be achiral, there is no provision for the origination of an enantiomeric pair. So for this compound, enantiomeric pair is absent. For these compounds, sorry, these compounds are optically active because of the provision for this enantiomeric pairs. But the last compound, the trans compound, is not having that provision, being it is symmetrically what the plane of symmetry is present within the molecule. Therefore, let me count the possible enantiomeric pairs: 1, 2, 3, 4. This is one enantiomeric pair. This is another enantiomeric pair. Two pairs are possible in terms of enantiomeric pairs. If stereoisomers taken into consideration, 1, 2, 3, 4, 5, all 5 are called stereoisomers only, right? So 5 are the stereoisomers, 2 are the enantiomeric pairs, right? So that is provided in the option number 1, 5 and 2. The correct number of stereoisomers are 5. The correct number of enantiomeric pairs are 2. That is given in the option number 1. For question number 66, option number 1 will be the correct answer. Let me move on to question number 67. For the complex nickel or NH2 taken 6 plus 2, nickel or NH2 taken 6 plus 2, R is meant for the alkyl functionality, delta naught indicated for the octahedral complex. It's the octahedral complex barycenter energy that is provided as a 12,600 centimeter inverse, and the spin orbit coupling constant indicated with the lambda for nickel plus 2 complex ion is minus 315 centimeter inverse. The mu effective values in a Bohr magnetons for the complex is closer to mu effective value to be calculated for this octahedral complex of the nickel, and whose delta naught value and the spin orbit coupling constant value is provided. Then how it is calculated, let's see. Magnetic moment of octahedral nickel plus 2 complex. The nickel plus 2 is an octahedral complex. We have amino functionalities around the nickel, monodentate ligands. Obviously, there will be a kind of a perfect octahedral complex will be originated, and it is the di-positive cationic complex. Within this complex, nickel existing in a D8 electronic system configuration. Octahedral complex ground state D8 system will be there, and here the representation of this term symbol will be 3A2G. 3A2G term symbol is provided. This state has a negligible orbital angular moment contribution. L value is becoming 0, right? 3A2G term. So here L value is 0 for this one, means that magnetic moment ideally closer to the spin only value. Though they are asking for the spin orbit coupling values provided, but orbital contribution is 0. Only spin only value is meant for this kind of nickel octahedral complex. However, 3A2G ground state mixes with the excited 3T2G state. Spin orbit coupling is possible for that one, which partially produces orbital angular momentum, slightly increases magnetic momentum value above the spin only value. Actually, at the ground state only provision for the spin only, but if you are exciting that one, so excited state, there is a provision for slight rise in the spin only value, being orbital contribution is also taken into the part over there. At that condition, the effective magnetic moment mu effective is corrected. Spin orbit coupling is given by the formula. Mu effective is equal to mu 1 minus 4 lambda by delta naught is provided. So mu SO is the spin only magnetic moment. SO stands for spin only magnetic moment. We need to consider. Lambda is nothing but spin orbit coupling constant value that is provided. We know that value. Delta naught, obviously, crystal field splitting energy. value is provided, right? So if this is the theory, in order to calculate that kind of problem, magnetic moment calculation for the octahedral nickel plus 2 complex. So let me go with the problem solving strategy now. So as we already were, nickel plus 2 octahedral complex existing, nickel existing in D8 system, and number of unpaired electrons are 2 only, right? D8 system, 2 electrons are located, unpaired electrons are 2 located over there. Spin-only magnetic moment, always spin-only magnetic moment is attributed by the odd electrons only. So this 2 is taken into the consideration under root n into n plus 2 by under root n into n plus 2 Bohr magnetons, the value is. So if n is nothing but number of odd electrons present in the compound, you can go with the substitution with 2, being a nickel plus 2 D8 system is having 2 odd electrons within the system. So mu spin only value will be under root 2 into 2 plus 2, that is under root 8. Root 8 value is indicated as 2.8 Bohr magnetons. Ground state nickel plus 2 Bohr magneton value will be attributed by the spin only, that is 2.8 Bohr magnetons. It's very clear. But we have excited state within the compound. So that's the reason why there is an orbital contribution. There is a provision for the calculation further. So mu spin only just calculated as 2.828 Bohr magnetons, and delta naught value crystal field splitting of octahedral complex is indicated as 12,600 centimeter inverse, and lambda value spin orbit coupling constant values minus 315 centimeter inverse provided. Right. So if this is the data we already had, the formula for the mu effective calculation is mu spin only into 1 minus 4 lambda by delta naught, where you can substitute mu spin only value 2.828, 1 minus 4 into minus 315 centimeter inverse by 12,600 centimeter inverse. Whenever you can go for the calculation, entire numericals calculation taking place, and simply the term is becoming minus 0.1. Mu effective is equal to 2.81 into 1 minus 0.1, the value is. So this term value is provided. So whenever this is the case, 2.828 is the spin only value into 1 minus 0.1 if taken, the value is becoming again 2.828 only. 828 into, so here minus becoming plus, so that here the value is into 1 plus 0.1, that is nothing but 2.828 into 1.1. Final calculation is 3.109, slightly above than that spin only value. Mu effective value is 3.109 Bohr magnetons. So here the calculated value is 3.109 and observed value is 3.11 Bohr magnetons. It is very closer to this 3.11 Bohr magnetons. Let me see where it is located. That is very closer to option number 1. For question number 67, option number 1 will be the right answer. Hope you got the answer. This is a question taken from the inorganic chemistry. Moreover, coordination compounds. Octahedral coordination compound with the nickel was taken. Magnetic property calculation was taken. Mu effective calculated by taking their spin only value and crystal field splitting value, spin orbit coupling as well. So if you are substituting all the values, you can achieve this value mu effective as 3.11 Bohr magnetons. For question number 67, option number 1 will be the correct answer. Move on to question number 68. A self-exchange rate and reaction potential for the following redox couples are given below. R value is the gaseous constant value 8.314 joules Kelvin inverse mole inverse. Faraday constant value is also constant, that is 96,485 coulombs per mole, right? This is the problem we are discussing. So if this is the case, self-exchange rate, mole inverse, second inverse is provided. Standard electrode potential values in the volts provided. Cerium is going to shift from +4 to +3. Higher oxidations to lower oxidation, obviously it is the kind of reduction process. And the self-exchanging rate value is provided as 4.0, whose standard electrode potential is calculated as 1.70 volts. If iron was taken, iron +3 to +2 got converted, and self-exchange rate will be 3 into 10 to the power 7, and whose standard electrode potential value is indicated as 1. If this is the case, we are going to react cerium +4 with iron phenanthrene +2. This is the complex. This is the metal ion. This is the complex. Both are supposed to be treated together. Whenever the reaction taken in between, cerium +4 is becoming cerium +3. So that reduction obviously taken. And here is the Fe +2 converted into Fe +3. Fe phenanthrene +2 complex now shifted into Fe phenanthrene +3 complex. Obviously, there is an oxidation, and you can designate the reaction as a redox reaction in between cerium and iron complex. For the above reaction, approximate rate constant at 25 degrees centigrade is calculated. So we need to go for the calculation of kinetics of the coordination compounds. So here is the question related with the kinetics, physical chemistry of the coordination compounds we are discussing with. So rate constant to be calculated in this value. Minute inverse, second inverse values are required to be calculated at 25 degrees centigrade. For this purpose, we have the calculation strategy here. Marcus cross rate relation is provided. The Marcus cross rate relation is used to estimate rate constant value that is provided as K12 for electron transfer reaction between two different redox couples based on their individual self-exchange rate constants K11, K22. So here, individual self-exchange reaction K11, K22, they are mentioned with, and reaction equilibrium condition, if both the reactions are in the equilibrium, that is indicated with K12, right? So here, individual compounds like cerium +4 to +3 is indicated with the K11, and iron phenanthrene complex self-exchange rate is indicated with the K22. If this is the case, in between, both are existing in the equilibrium, that is indicated with K12. The simplified formula will be K12 is equal to under root K11, K22, K12 was taken. The equilibrium constant K12 is derived from the standard potential delta E naught of the reaction using Nernst equation. Nernst equation for this K12 equilibrium rate constant will be e to the power nf delta E naught by RT. E to the power nf delta E naught by RT will be taken, where n meant for the number of electrons transferred during the redox reaction, F is the Faraday value which is provided within the problem, R is the gas constant that is also given for value only. T is the temperature on Kelvin scale. Delta E naught is equal to E naught oxidizing agent minus E naught reducing agent. So here the difference in the standard electrode potential is equal to standard electrode potential of the oxidizing agent minus standard electrode potential of the reducing agent to be taken. The difference is called delta E naught. If this is the case, how can we go for the calculation? Let me see. Cerium +4 is going to react with iron phenanthrene +2 complex, so that cerium got reduced, iron got oxidized. Given value, transfer of electrons is only 1, so that N is carried as 1 only. 1 electron transfer reaction, the entire reaction carried at 298 Kelvin temperature. K11 self-exchange reaction for that cerium was given as 4.0 for the cerium, and K22 is given as 3 into 10 to the power 7. This is for iron phenanthrene +3 +2 conversion self-exchange. In case of E naught, standard electrode potential of the cerium is given as 1.70. Standard electrode potential of that iron phenanthrene was given as 1.00 volts. So if the value of RT by F, that is entirely fixed because rate constant may not be changed, Faraday value may not be changed, temperature may not be changed. That is taken as a 0.02569 volts at a 298 Kelvin temperature, right? So here you can simply write this as 0.0257 volts. F by RT, if you are reverting the equation, that is becoming 38.92 volt inverse. The value is totally inverted. We are reversing the terms totally. So the 38.92 volt inverse we got at 298 Kelvin temperature. Calculate the standard cell potential E naught value. So delta E naught value to be calculated. In order to calculate delta E naught E1 naught minus delta E2 naught, E1 naught minus E2 naught difference to be taken. Here, for the first one, 1.70 volts we have. For the second compound iron complex, we have one value. 1.701, the difference will be 0.70 volts. This is what a different standard electrode potential, delta E naught value calculated. Equilibrium constant K12 to be calculated. In order to calculate K12, the formula will be e to the power NF delta E naught by RT. N value is 1. Faraday value already included within. And here is the E naught. Delta E naught value just calculated as 0.70 volts. And F by RT value totally that is indicated as 0.02569. Right. So here 1 into 0.70 by 0.2569, nothing but 27.24. So here 27.24 taken for the e to the power. So that's the reason why K12 is equal to e to the power 27.248. So this is the e to the power. If you are going with the calculation of this one, this e power calculation, after the calculation you got the value 6.81 into 10 to the power 11. That is K12 value. Let me show whether you got that answer within the complex. That is a rate constant at the equilibrium. We got this value. After getting that one, calculate the cross rate constant. Cross rate constant is nothing but K12 is equal to under root K11, K22, K12. The entire values to be taken, that is cross rate constant. So K11 is known to you, that is 4.0, and K22 is known to you 3 into 10 to the power 7. K12 value just calculated as 6.81 into 10 to the power 11. If you are calculating the entire values, we got K12 is equal to under root 81.72 into 10 to the power 18. K12 is equal to 9.04 into 10 to the power 9. Calculated value is 9.09 into 10 to the power 9, approximately 0.9 into 10 to the power 10. 9.04, you can write it as 0.904 into 10 to the power 10 as well. The value is very closer to, this value is very closer to 1.1 into 10 to the power 10. 0.9, 1.1 exactly, almost, not exactly, almost similar. That is provided in the option number 1. For this question, option 1 will be the correct answer. It is somewhat complicated converting the entire this coordination chemistry into kinetics. It is difficult. We need to know the formula, then only it is possible. Simplified formula to be known, that cross rate constant value is equal to K11 under root K11, K22, K12. This to be known to you later on. So K11, K22 is known. K12 value is calculated by taking e to the power NF delta E naught by RT. So if you are calculating this one, you can put over there so that you will get K12 value, that is taken as option number 1. After this one, let me move on to another question. Again, it is the part of that physical chemistry only, mass bar spectroscopy. Analytical chemistry part, it will be not physical, sorry, analytical chemistry part. The mass bar spectra of iron L2I2. So here is the kind of complex you can notice. Iron complex was taken. The ligand whichever manifested within the iron complex sphere will be 3,5 dimethyl tris pyrazolyl borate. So it is the dimethyl tris pyrazolyl borate kind of ligand taken within the sphere. and exhibit temperature dependent spin transition behavior. So this kind of temperature based transition is possible. If you are taking the spectrum at 295 Kelvin, you will get the doublet like this. If the temperature varied like this, you are reducing the temperature to 166 Kelvin, there is a increase in the peak number. You got 3 peaks within the same compound. If the temperature is still reduced extremely lower, 4.2 Kelvin temperature if taken, all the peaks got merged and you got only single peak with the same compound. So that only the difference you noticed is the temperature variation. So that the spin transition may taken by the temperature variation only. If that is the case, the correct statement from the following. So here, if this is the spectrum you got that from the spectrum. So what statements are correct among these A, B, C, D, E options? At 295 Kelvin, iron plus 2 center is high spin. At 4.2 Kelvin, iron plus 2 center is low spin. At 295 Kelvin, iron plus 2 center is low spin. At 4.2 Kelvin, iron plus 2 center is the high spin. At 166 Kelvin, represent mixture of low spin and high spin together, Fe plus 2 complexes. These many options are provided. What are exactly correct? We need to identify. That identification requires first problem analysis. We need to analyze the problem. The question taken from the analytical chemistry, mass bar spectroscopy. Mass bar spectroscopy and spin states of the iron plus 2. Obviously, iron plus 2 existing D6 system. And being we had that chelating ligand, that's the reason by low spin it will be. And the high spin may possible configuration depending upon the ligand field strength and the temperature as well. Isomeric shift is possible. Quadruple splitting is also possible for mass bar spectra. So by using this isomeric shift and quadruple shift, it is possible to distinguish low spin Fe plus 2 complex, high spin Fe plus 2 complex as well. Same ligand, same metal, but the complex nature will be varied. There is a provision for low spin and high spin as well. Low spin plus 2, low spin iron plus 2, lower isomeric shift and the smaller quadruple splitting due to the symmetric electronic distribution is possible. Isomeric shift will be lower. Quadruple splitting is also a kind of a possibility for the low spin Fe plus 2 complex. If the Fe plus 2 existing in high spin, the provision is higher the isomeric shift and larger quadruple splitting is also possible. So if this is the case, the complex existing in high spin Fe plus 2 nature. Temperature decreases, system can shift from high to low spin now. Right, spin states of the iron plus 2 D6 and electronic symmetry. So here the how the spin state got shuffled with this electronic symmetry we need to understand. Fe plus 2 has a 3D6 configuration and octahedral ligands are there. 5 d orbitals are splitting into T2G Eg, being it is octahedral splitting. T2G obviously go to the bottom region so that they are acquiring the lower energy and being T2G stands for triplet degenerated orbitals, so that here 3 orbitals laying at the bottom. Eg orbitals are rising up energy in the octahedral complex field. That's the reason why higher energy 2 orbitals are located doubly degenerated. 2 spin states are possible based on the ligand field strength, high spin and low spin. High spin is located for this complex whenever weak field ligands are located within and electrons spread across the all 5 d orbitals. Instead of pairing of electrons, all electrons within the molecule within the complex will go for the occupation of the entire orbitals. All 5 orbitals got occupied. So, but in case of low spin, strong field ligands are present. Pairing of electrons are taken within the T2G orbital only if less number of electrons are present. All 6 orbitals when filled in the bottom level T2G, then only the next electron will go for the occupation in the Eg orbital. After the pairing of all orbitals in the T2G, then only the next coming electron go to the higher level energy Eg. So unpaired electrons may not be possible for this kind of low spin being all are paired up. This is the way a kind of two provisions we noticed, high spin and low spin. At the high spin condition, you can find four unpaired electrons. In the complex low spin, it is existing in low spin, zero unpaired electrons are possible for that kind of iron plus 2 complex. If you're observing temperature dependence for the complex behavior, right? 295 Kelvin temperature if taken, mass gas spectrum shows the larger quadruple doublet. That's the reason why high spin Fe plus 2 is possible at this condition. If you're shrinking the temperature to extremely less, 42 Kelvin temperature, doublet is becoming very short and narrow itself, indicating low spin Fe plus 2. Initially, high spin complex totally inverted into the low spin complex whenever temperature is extremely less, 42 Kelvin. If you go to in between, that is 166 Kelvin temperature, two overlapping doublets are visible. This is the mixture of high spin and low spin. This is not completely high spin, not completely low spin. You can resemble the shades of high spin and low spin in the same compound. So spin transition is noticed at this 166 Kelvin temperature. High spin Fe plus 2, configuration T2G4 and EG2, being all the electrons are freely moving to T2G and EG, and all are singly occupied electrons only. Electron distribution is asymmetric, and unpaired electrons are entering into the EG as well. Due to the axial asymmetry in the electronic field gradients, the mass bar larger quadruple splitting is possible. Higher isomeric shift is noticed for this kind of complexation that is available at 295 Kelvin. And low spin, we are treating with 42 Kelvin temperature. Configuration is resided, all six electrons present in the Fe plus 2 are resided in T2G orbital only. Electrons are fully paired in T2G, giving us spherical symmetry. No axial asymmetry, smaller quadruple splitting, mass bar narrower splitting, you noticed lower isomeric shift is possible. This explains the change in mass bar spectra of the temperature for Fe plus 2 complex undergoing spin crossover transition, right? If this is the case, what answers are correct we need to identify. At 295 Kelvin, higher temperature, Fe plus 2 center is high spin, correct only. At 4.2 Kelvin, iron plus 2 center is low spin, obviously correct. 295 Kelvin, Fe plus 2 center is low spin, wrong. 4.2 Kelvin, iron plus 2 center is high spin, wrong again. And 166 Kelvin represent mixture of a low spin and high spin together is also the correct. A, B, E are correct. A, B, C wrong. A, B, E are provided in the option number 4. For this question, option number 4 will be the correct answer. Move on to next question. Question number 70. We are dealing with question number 70. The electronic configurations showing tetragonal compression and elongation in their octahedral complexes respectively are. This is the form of distortion of the orbital geometries, right? The electronic configuration which is undergoing tetragonal compression and elongation in the octahedral complexes respectively. So that is possible with what kind of electronic configuration we need to identify. John-Teller distortion taken into the picture. John-Teller distortion is also the is only the reason for this compression and elongation. John-Teller theorem states that only non-linear molecular systems with the electronic configuration state orbitally degenerated will spontaneously distort in their geometry to remove the degeneracy and they achieve the lower energy. So whenever the kind of degenerated orbitals distortion taken place, non-linear molecular system are taken for this consideration. Whenever non-linear molecular systems were there and orbital degeneration is possible, so that here degeneration is totally lost within the compound. This distortion is most commonly observed for octahedral complexes where e.g. T2G orbitals are unequally occupied. Symmetrically unequally occupied system when present, then only Tiller operation is possible, leading to the degeneracy, distortion, lowering the symmetry, octahedral 2, D4H, tetragonal distortions are possible. If you want to get the tetragonal elongation, Z out, Z axis longer, Z orbital axis electrons got elevated, their bond distances got longer, and this elongation taken because e.g. orbitals degenerate and occupies the one electrons. Whenever D9 system and low spin D9 system, either it may be low spin or high spin. If D9 system is there, there is a possibility for the tetragonal elongation. And low spin with the D7 system, there is a provision for the tetragonal elongation. These two are satisfying with the tetragonal elongation. The electrons preferentially occupy the lower energy dz square orbitals and leaving dx square minus y square empty. This results in a weak metal ligand bond x-axis. Along the x-axis, metal ligand z-axis energy got raised up. Metal ligand xy orbital energy got lowered because of this John-Tiller distortion, so that your z-axis ligands got elongated. Tetragonal compression, this is a reverse of this elongation process. Z in, z-axis shorter taken place. Z-axis orbital, axial orbitals shrinked. This is possible whenever T2T orbitals are degenerated with the D1 or low spin D4 electronic system. D9 and low spin D7 corresponding with the tetragonal elongation. And D1 and low spin D4 systems are tetragonal compression process taken place. This results in a stronger metal ligand bonds along the z-axis. So this is giving rise to John-Tiller distortion, tetragonal elongation, and compression. In accordance with the data which were known to you, the electronic configuration with the D1 showing the tetragonal compression, whereas D9 is showing tetragonal elongation in accordance with the John-Tiller distortion, which is giving option number 2 is the correct answer. Here, the electronic configuration showing tetragonal compression taken with the D1 system, elongation taken with the D9 system in the octahedral complex respectively, that is provided in the option number 2. For this question number 70, option number 2 will be the correct answer. John-Tiller distortion based question. It will be, again, it is a part of inorganic chemistry in specific coordination compounds. Let me go on to question number 72, the correct match between the enzymes and their enzymes in the column P and their biological functions in the column Q from the table below. So enzymes and their biological activities are manifested in the two different columns. Column P, we have cytochrome C oxidase, tyrosinase, purple acid phosphatase, galactose oxidase, ribonucleotide reductase. All these are provided in the column number P. If you are moving on to column number Q, DNA biosynthesis, hydrolysis, oxidation of phenols, oxidation of alcohols, reduction of oxygen to water. These are the enzymes. These are their biological activities. Which is correctly mapping this, which one, we need to identify. For that purpose, we have a theory. Cytochrome C oxidase, if this is the enzyme, what activities it possesses, let me show. As a final enzyme in the electron transport chain of the cellular respiration. In the cellular respiration, it will be the enzyme for the purpose of electron transport. Catalyzes the transfer of the electrons from the cytochrome C to the molecular oxygen O2. Its main function is the reduction of oxygen to 2 molecules of water. All right. In addition to the electron transfer, reduction of oxygen into the water formation is also possible. This reaction conserves the energy by pumping protons across the mitochondrial membrane. Mitochondrial membrane pumping of protons are also possible with this, right? So this is regarding the cytochrome C oxidase enzyme. If tyrosinase is the enzyme provided, the activity of this one will be copper containing enzyme. It will be copper containing monooxygenase enzyme, polyphenol oxidase enzyme. It will be catalyzes oxidation of phenols like tyrosine into orthodiphenyls. It also catalyzes further oxidation of orthophenols to orthoquinones. Key enzyme involved in the biosynthesis of melanin. Melanin is a pigment, right? So here is the purpose of tyrosinase. Tyrosinase will be the oxidation of phenols are possible, although diphenols will be the products by means of this enzymatic action. Purple acid phosphatase, if enzyme provided, what activity it possesses? A metalloprotein known for its characteristic intense purple or pink color in nature. It belongs to the class of phosphatases. It functions to catalyze the hydrolysis of phosphate ester bonds, phosphoproteins, and nucleotides. If you are considering nucleotides and phosphoproteins, in that hydrolysis of these esters are taken place by means of this phosphoacid phosphatase, purple acid phosphatase enzyme. This activity releases inorganic phosphate. So inorganic phosphate will be released by means of this hydrolysis process. This is the way phosphatase enzyme is working. Move on to D, galactose oxidase enzyme. A copper containing enzyme, it will be a type of oxidoreductase enzyme. Oxidoreductase enzyme, it will be catalyzes oxidation of primary alcohol into galactoses. Other primary alcohols also got reduced with this process. Specifically, it converts the alcohol into aldehydic one, right? Alcohol to aldehyde is the oxidation process. It will be, and concomitant reduction of the oxygen into hydrogen peroxide is also possible, right? So here the process of oxidation, here the process of reduction, both are taken by the same kind of enzyme called galactose oxidase. That's the reason it is called oxidoreductase enzyme. Probability for alcohol to aldehyde said to be oxidation. Oxygen to hydrogen peroxide, it is said to be reduction. This galactose oxidase is available in the fungi involved in the fungal defense, right? So fungal defensive activity is mainly due to this enzyme existence. Ribonucleotide reductase, it is the another enzyme, critical enzyme for the DNA replication and repair process. Whenever DNA got damaged, at that condition, ribonucleotide reductase is the enzyme will work and it will repair that injured DNA. Catalyzes reduction of ribonucleotides like ADP and GDP, adenosine diphosphate, guanosine diphosphate. Two, the deoxyribonucleotides are generated, DADP, DGDP formation is possible. The product deoxyribonucleotides are essential building block for the DNA biosynthesis. This is the most crucial enzyme in our DNA biosynthesis process. Uses free radical for its catalytic mechanism. The entire process is mechanized by the free radical process, right? This is the way all the enzymes are having their distinctive applications in the field of their biological functioning. That's the reason why cytochrome C oxidase is meant for terminal enzyme electron transportation and responsible for the conversion, means a reduction of oxygen into water taken. Tyrosinase is meant for polyphenol oxidase process, and it initiates the melanin synthesis within the materials and catalyzing oxidation of phenols, specifically tyrosine diphenols are generated. Purple acid phosphates as phosphatase that cleaves phosphate ester by the hydrolysis process, releasing inorganic phosphate. Free inorganic phosphate will be released. Galactose oxidase is oxydoreductase that specifically oxidizes C6 primary alcohol into the aldehydic compound. Galactose aldehyde will be originated. Ribonucleotide reductase is a very essential enzyme in conversion of ribonucleotides into deoxyribonucleotides, providing precursor in the DNA biosynthesis. All these are available in the option number 3. Let me go with the question. Cytochrome C oxidase is meant for this reduction of oxygen into water taking place, so that A to be mapped with 5. Tyrosinase is meant for oxidation of phenols taken. Tyrosinase is made for oxidation of phenols, and the purple acid phosphatase is taking the part of this hydrolysis. Galactose oxidase is made for this oxidation of alcohols. Ribonucleotide reductase is made for the DNA biosynthesis. A with 5, B with 3, C with 2, D with 4, E with 1. All are provided in the option number 3. For this question, option number 3 will be the correct answer. Let me move on to last slide. I would like to say my heartfelt thanks to all the viewers who ever taken your precious time to watch the entire session, and hopefully I gave the informative session for you and in-depth knowledge regarding the how to solve the question paper and the content which is taken from the authentic websites, and watch regularly. You can achieve definitely kind of aspiration whatever you are having towards the competitive exams or any kind of entrance examination as well, and even research purpose also. This kind of session is very much helpful, and you can subscribe the channel Dr. Kavitha Kotireddy Kota and share with your friends. Subscribe, watch regularly, watch complete the video so that you will get the sound knowledge regarding the chemistry, and definitely you will achieve the success in your field. Thank you very much. Signing off, Dr. Kavitha Kotireddy Kota.